Okay, next we go to the master slave flip-flops. Okay, so you can see this one. So the master slave flip-flops is introduced to overcome the timing problem that might be occurred to the flip-flops. Okay, this means we have two similar flip-flops are connected with different clock lah. This is, for example, we have D flip-flops. Okay, we have one flip-flops and another one flip-flop lah, but we have the different clocks. Okay, for example, the D flip-flop first with the positive, okay, edge trigger, and then second will be negative edge trigger lah, because this one, remember this one, we have the bubble here. That means for the second D flip-flop, we connect to the negative edge trigger. Alright, so this is the output lah. Okay, this the output Q will be connected to this one lah. Alright, to this point it can ignore this one. Alright, so you can see is the Q1, Q0 and Q1. Alright, so you can see this some example here. So you can see the first D flip-flop, we focus on the positive. Alright, this one, the Q0 here, the Q0 here, we focus on the positive, and the Q1 here will be focused on the negative edge trigger on this part lah. Alright, so but the D here, okay, for D on the second D flip-flop is refer to the Q0 here. Okay, the Q0 here. Alright, so this one actually the input for the second D flip-flops. Okay, if we go for the first Q0 here, so for example, okay, this one D1 will be 1 here, and then until to next active here, positive lah. So next D is 0 here, 0 here, that means here all will be 0 until the next cycle active, the clock will be active here. So D is 1. Alright, it will be 1 here, and last one will be 0 lah. Okay, 0, this one will be 0. Okay, and then for the Q1, okay, the Q1 refer to the negative edge trigger here. Okay, but the D actually is the D the refer to the Q0 lah. Okay, the Q0 here, so D is 1, so automatically you got 1 here until the next cycles active. Okay, on the negative edge trigger here, D is 0. Okay, that means Q0 is a 0 here, so that's why you get 0 here. Then the next, okay, next is the D or Q0 will be 1, so automatically we got 1 here lah. Okay, this is we call the master slave flip-flops. Okay, this is some example lah, D latch and versus D flip-flops. Okay, for example, this is circuits. Alright, they're connected to the same clock lah. For example, this one, clock will be same clocks. Okay, this one will be positive. Okay, this one is using the latch. Okay, this one using the flip-flops. Okay, this is positive edge trigger, this one will be negative edge trigger. Alright, so this is our input output lah. Okay, output QA and QA bar. Alright, so this is time diagram lah. We can plot. Okay, we can refer to the D latch and D flip-flop. The output will be similar lah. Okay, will be the output will be refer to the input lah. Okay, based on the clock. Okay, based on the clock. Alright, so the synchronous preset and clear. So before this, we thought that we know about the timings. Okay, timing signal for the flip-flop is we have two type lah. Okay, we have two type. First is synchronous, second is the asynchronous lah. For asynchronous, they have preset and clear. Okay, you can see on this is some examples of the T. Okay, T flip-flop. We have this one, we have the presets and we have the clear here. Alright, so this is active lah. We have the bubble here. Alright, so you can see the table here. Okay, for example, if preset we have 0, clear will be 0, so the operation will be invalid. Okay, we call that invalids. Okay, if preset is the 0 and then clear is 1, so automatically the operation is set lah. Set, that means Q is 1. Right, if preset 0, okay, and then clear is preset is the 1, clear is a 0, that means the operation is the resets. And then if preset is 1, clear is 1, so that is the flip-flop normal operation lah. Okay, this is some example. You can see this one. So this one T. So this one will be toggles. Okay, will be toggles here. Alright. So next you can see this one. So next is the T0. No change because clear is still okay. So until this one clear here, still not active, clear. That's why it got no change. But until this point, so you can see the clear is 0. So that's why the clear is 0. So will be reset lah. Okay, this one will be reset because of the clear is 0. This one will be reset until this point lah. This point will be until this point will be toggles. Okay, will be toggles. Alright, until this one okay will be toggle lah. Okay, will be toggles because of T is 1. Okay, you have to remember the operation of T is toggles, and then will be preset. Okay, because of here. Okay, here will be preset so will be preset. Okay, can see this one because of the our preset will be 0 here. Okay, you can see so if preset 0, activate the preset lah, the output will be set high. Okay, and then if for example the clear is 0, activate the reset lah, so will be reset lah. That means will be reset to be 0 Okay, so this is some flip-flop operation characteristics. Alright, you can see first we have the propagation delay times. Okay, so the propagation time is the required time interval for the output signal to occur after an input signal have been applied lah. Okay, for example you can see this one this is our clock. Okay, actually this is normally if you refer before this, our clock similar like this but if you zoom here, okay, if you zoom here using the, maybe you can zoom. Alright, so you can get like this, similar like this. Normally it's not straight line it's just something like this. That's why you get from this point is the 50%. Take from this one to 50% to the Q, to the output will be 50%. This one we call the propagation delay high. Okay, this one high and this one will low. You can see this one this is our clocks, and then this is on the positive. Okay, on the positive positive edge trigger, so we can call the propagation delay high, time propagation delay high, and then this one lower because on the negative. Okay, we can take on the negative from clocks to the negative edge trigger. Alright, and then the setup time is the minimum time interval for the signals to retain the value before clock pulse is triggered. Alright, so this is we call the time setup. Okay, this is our D, and then this is our clock. So you can see the 50% to 50% here we call the TS lah. TS time setups. Okay, and then next we have the hold time. So, okay, hold time is the minimum time interval for the signals to retain the value after the clock pulse is triggered. Okay, so this is our clocks and this is our D. So this one 50% to this one 50%. So this one we call the hold time. Okay, hold time. And then next we have the maximum clock frequency. Alright, so from this, actually from this point to this point to calculate the frequency. So the maximum clock frequency, the highest rate at which the flip-flop can respond to the input signals. Okay, so another characteristics such as pulse width. Okay, pulse width, minimum clocks pulse width is smaller time between the high and low. Okay, that is we call the pulse width. And then the power dissipation. Okay, the total power consumption of the flip-flops. Okay, this is some example lah. We use the 474 chips that have 2 D flip-flop, which each of the flip-flop operate at positive 5 volt DC and draw 5 milliampere. Alright, so for example we know the formula of power is P equal to IV. Okay, IV or VI. Alright, it's similar. So this is VCC, and then multiplied by ICC, voltage multiplied by ampere. Alright, equals to, so we know this one is the 5 volts, and then this one 5 milliampere. so the power will be 25 milliwatt. Okay, and then because we use 2 D flops, okay, 2D flip-flops, so we have to multiply by 2. We got 50 milliampere. Alright, using this formula, okay, using the same formula to get the current total here. Current total, this is current power total, and then this is current total. That means the power divided by voltage, so you can get the current total lah. So current total 10 milliampere. Therefore the chip must be supplied by 5 volts DC supply with at least 10 milliampere of the current lah. Okay, next we go for the flip-flop application.